I'm Hannah. I'm a postdoc at Edinburgh University, and I've been part of IGAC for a couple of years now. But we have a really big team who've been organising this conference, and this is sort of a picture of everyone. So we're very grateful to everyone who has been a part of organising this conference. And if you run into any trouble today, please just find one of these people on GatherTown, send them a message, and everyone is more than happy to try and help you figure out your way around things. But yes, we have a great, very globally diverse team, and that's been amazing for organising a conference over 3 different time zones in this 19-20-hour extravaganza of a conference. A little bit about IGAC. So there's a lot of acronyms being thrown around in this conference, and you might have noticed in the main hall there's a lot of posters with acronyms that make maybe not much sense, but this is sort of our breakdown of what most of them mean. So essentially, going right back to the International Science Council, this became the International Union of Geodesy and Geophysics, UGGI, and then from that we had IAMAS, the International Association of Meteorology and Atmospheric Sciences. IAMAS is one of our sponsors for this event, so we're very grateful to them because they've made it possible to have some of our prizes which we're able to offer. And then we have ICACGP, which is the Commission on Atmospheric Chemistry and Global Pollution. And then finally IGAC, which is celebrating its 35th year this year because it was made in 1990. We've also on here got some sister organisations, so iLeaps and SOLAS, which look at land ecosystems and then surface ocean respectively, and they've both got some posters up in the main hall. So if your field of study might fit, with one of those a little bit, please go and have a look and see if you can get involved, because they're great organisations that are sort of the sister to IGAC. And I will hand over to Simone.
Hi everyone, I'm Simone. I'm a postdoc at the Max Planck Institute for Chemistry in Germany and part of the organizing committee, as well as co-chair of the IGAC-iCACGP Early Career Researcher Scientific Steering Committee, which is the committee you see on the screen now. We run workshops and seminars throughout the year, and then we have a newsletter that we also send out every month. So just a couple of short announcements from the SSC. We have a new funding opportunity coming up. So we are starting our own small grant only open to early career researchers, and that will be having its first open call this October. So you can apply for seeds for like seed funding to support your research, going to conferences, summer schools, but there will be much more information on that in our newsletter. And we will also be recruiting new members for the 2026 committee. So that will also be more, there will also be more information on that in the newsletter. And if you haven't already signed up for it, you should scan the QR code down in the corner, and then you can sign up for the newsletter. And one of these workshops I was talking about, the next one upcoming is with Colleen from OpenAQ. She's going to talk about how we can use OpenAQ for air quality research and applications in the end of October. So if you're interested in that, you should sign up for the workshop. And then you can keep up with us on our social media and our website. So all the social media tags are at the bottom. For today, we are right now having this welcome, and then we're going to have 3 highlight talks. Then we're going to switch over to do an icebreaker, a skills workshop, networking, and then we're going to do poster session number 2, not 1. So for this Q&A, during the highlight talks, there'll be a Q&A button at the bottom of your screen. So if you have any questions, please put them in there and upvote if there's a question that you agree with that somebody else have already asked. During all the more interactive sessions, please turn on your camera and microphone while you have conversations with the people. If you have any problems in GatherTown, find the people that have organizing committee written underneath, as you can see out in the picture on the right. And if you sign up for your poster to be evaluated, remember to be at your poster at the allocated time. If you think you haven't been evaluated, please also come and find someone from the organizing committee and let us know. And if you need a certificate for presenting your poster, you can go to the certificate stations during the poster session and sign up for that, but it's only open during the poster session. And then have fun, network with the people, and keep in touch with them afterwards, maybe through LinkedIn or other social media. So these is our invited speakers, and Vaishnavi is going to introduce you to them later, and our skills workshop hosts as well will be introduced during our skills workshop later.
And then just very quickly to show you the Gather Town layout. I know a lot of you have already been having a look at the poster room in the last session, but we just want to draw your attention to, in the main room, we've got a lot of these boards which you can have a look at, and they are a range of working groups, international activities. Some of them are country specific or theme specific, but please have a look at them because they can contain a lot of information of groups you might be able to get involved with. We've also, in the bottom right hand corner, got some of our funders, and you can have a look at what they get up to. A lot of them are very linked to the IGAC mission as well. And as you can see on the right hand side is the poster room. If you're struggling to interact with the poster, press the X button. And then at the bottom is the plenary room. And then on the left is the side meeting room. So that's where we're going to go, like Simone said, for the icebreaker and things like that. And then finally, these are our funders. We're really grateful that we've been able to get so much support for this conference because it has meant that we're able to offer our poster prizes. So we're offering 6 prizes, and they'll cover the accommodation, registration and travel to IGAC 2026 in person in Greece. So a big thank you to everyone who's made that possible. And with that, I will hand over to Vaishnavi for the highlight talks.
Hello, everybody. Hope you're doing great wherever you are. This is Vaishnavi. I am a research scholar here at the National Atmospheric Research Laboratory, and I'm here to introduce the session speakers for today. So first up, we have Dr. Zanchang Liang. Dr. Liang is a research scientist at King Abdullah University of Science and Technology in Saudi Arabia. His research focuses on the photochemical processes of atmospheric particles, with recent work on organic triplet state chemistry related to brown carbon aerosols and their impact on climate change. Today, he will present his work on biomass burning organic aerosols and their role in driving atmospheric reactions. Please join me in welcoming Dr. Liang. Zach.
Hello. Thank you, Vaishnavi. So, hello everyone. Thank you so much for the introduction by Vaishnavi as well as the scientific community. So, could you see my screen right now? I believe I do a screen. Oh,
yes,
yeah, perfect. Okay. So, hi again, everyone. So, this is Sankong or Zach from KAUST in Saudi Arabia. I work there as a research scientist, and today I feel very honored to deliver some interesting findings I got in the past few years related to the multi-phase photochemistry of wildfire aerosols. Okay, so I do believe everyone of here have like some understanding of airborne particulate matter and aerosols already. So I will directly cover some background related to biomass burning and And we see here the wildfire or forest fire as a major emission sources of biomass burning organic aerosols. And we will see upon burning, there is something dark, which is the smoke, and consists of numerous aerosols, which can scatter the sunlight in the classical view and also absorb the sunlight upon the recent finding in maybe the last 2 decades. So we'll be able to see that it has been heat up, which is the atmosphere, a physical prominence that considered as a potential positive radiative driver in the atmosphere in recent years. So these light-absorbing molecules or components are actually discovered as the aromatic organic molecules dominantly by research by Professor Alice Laskin. And also they will find that making a very great contribution, even comparable to those we are talking about black carbon in the Arctic region in the recent work. So as we just discussed, let me use the screen pointer. the brown carbon aerosols inside the BBOA has made great contribution to in the physical part of atmosphere radiative balance. So regarding the chemistry part, or let's say photochemistry, it has been largely overlooked. So let me revisit a little bit what the typical photochemistry in the atmosphere is considered as. So basically, it is photolysis, which is a prerequisite that the photon energy taken in by the molecule should be above the bond dissociation of molecules. So if we do a Planck equation which shows the photon energy as a function of wavelength, we will be able to see that, it gradually decreases as wavelength increase. And if we're talking about the overlapping region with the bond dissociation energy of typical atmospheric molecules, we definitely need like the wavelength below 320 nanometer, let's say short UV, to make effective photolysis happen. But somehow, if we look at the actinic spectra, which is covered like this, because the ozone layer quite above has absorbed most of the short UV, so if we want to have this short UV, we need to arrive at the UVB regions shown here, which actually only takes up less than 1% of the total UV available in our troposphere. So that means the effective photolysis is really, probability-wise, is not a very high case. So in typical atmospheric radiative models, also photolysis are sometimes considered as a processes determining the fate of brown carbon particles like BBOA. It is like less significant compared with the internal conversion and fluorescence. That means the overall processes has been largely considered as a reversible processes between the light and heat until around 2 decades ago, Professor Christian George, Marcus Arman, I guess Barbara Dahanna, they found that there are so-called intersystem crossing processes that will convert or alter the spin direction of the single-let excited state molecules and convert them into triplets. So due to the spin direction alternations, they are prohibited to be relaxed to the ground states via phosphorescence. So this afford them a relatively longer lifetime compared with single oxygens, and they can interact with other molecular species for reactions in the atmosphere defined as photosensitization. So a key message is that the brown carbon aerosol, or less specified to BBOA, are actually most likely more than just absorb light. When we know about that, they can act in a chemical way upon light absorptions beyond the light absorbing. But how come there are, after all, there is a major scientific question to answer. That is, how would quantitatively these light absorbing BBOA particles will initiate the triplet reactions, like the reactions triggered drive by the triplet species. So here I want to cover the major difficulties, which is the transient nature of the triplet species. If we do a comparison, we will find that the triplet species have lifetime actually far below 1 second. So why the typical atmospheric gases, including greenhouse gases or gaseous pollutants we are usually talking about for routine measurements, have lifetime more than minutes? This makes the direct measurement of triplets very difficult. But there is some atmospheric chemists, like Professor Cotta and Anastasio, they found a routine to measure the triplet steady state concentration indirectly. So basically, they introduce such type of prop molecule, which has a known reactivity with the triplets. And then they just buy the prop molecule in so-called aqueous solutions and monitor its decay upon irradiation. And then the slope of this decay plot refers to the product of the second order reaction rate constant between the prop molecules and the triplets times the steady state concentration of triplets. Okay, so we can retrieve the steady state concentration of triplet right now. But somehow this needs to assume our system is perfectly an ideal solution, which is difficult to achieve in a concentrated airborne aerosol particles. So how can we do that? So here comes my major part of work, my first part of work, which I utilize SO2, sulfur dioxide, which is a ubiquitous atmospheric gaseous precursors as a multi-phase probe to titrate or retrieve the reactivity of BBOA particles in set of solutions. So briefly, I try to burn the pine wood in the lab and extract them. Later on, I atomize them, do the stabilizations, humidifications, remove the VOC, and later on site selection in period of introducing them into such a UV aerosol flow tube reactors. So notably, we have a movable injector, so I can easily change the exposure time for the aerosol particles to light to do a quasi-kinetic. So SO2 has been carried by a nitrogen flow and interact with the BOA particle underlying this reactor. So we'll be able to see some results. So SO2, upon oxidation, they will form sulfate. And when we monitor the sulfate concentration in the particles, it gradually linearly increases with time, regardless of SO2 concentration and light intensity. So if we consider light intensity as an indicator for the availability or abundance of the triplet molecule excited states, a photochemical reactant, we see that the solid formation rate linearly related to the SO2 concentration as well as light intensity, which suggests that the reaction between the sulfur 4 in a dissolved form and the BBOA triplet can be considered as a second order processes like this. So the kinetic expression can be shown like this. The solid formation rate equals the second order reaction rate constant between the triplet of BBOA as a whole and the sulfur 4 and times the triplet concentration via the probing method in aqueous solution, and then later on I extrapolate to the aerosol conditions times the sulfur 4 steady state concentration derived from the thermodynamic equilibrium. To facilitate illustration, I just put this under this because I've been using different concentration of SO2. So I call this normalized solid formation rate equals to the pseudo first order reaction rate constant. I call this a modeled by the assumption of ideal solutions, and I found that the model solid formation rate perfectly aligned with the measurements in aqueous solutions, which is very dilute, perfectly ideal. And then this conclusion can be extended to large droplets with diameter of 1 millimeter. But somehow, when we try to look at tiny or smaller aerosol particles in the aerosol flow tube, the model underestimates the solid formation for more than 3 orders of magnitude. Okay, let me play more with the size. So I try to do select more initial size of the particle for introducing into the aerosol flow tube, and I also change the relative humidity a little bit to slightly change the size of the particles. But interestingly, I found the solid formation rate linearly correlated with the surface to volume ratio of the particle. Despite the low relative humidity, actually will get the aerosol particle viscous. So let's imagine SO2 comes from the gases. So if the particle gets viscous, they will have difficulties in entering the bulk via diffusions. So despite this, the prominent solid formation indicate that the reaction are most likely taking place at the interface of the particle instead of the bulk. So when we have the so before we arrive at the atmospheric implication, I want to show this paper by Professor Sheng Xiaojie and Professor Xi Guoliang from Nankai University, which find that the H2O2, among other classical pathways driving sulfate formation, it's a dominant pathway all over the world. Number-wise, it accounts for more than or close to 80%. And notably, and most of the Wi-Fi prone regions like the United States, Eastern United States and Canada, they are all dominated by H2O2. So this makes the thing easier because I can just compare the BBOA photosensitization pathway with the H2O2 pathway. So here I hypothesize 2 scenarios. One, a so-called moderate file with 10 microgram per cubic meter BBOA plus 10 microgram per cubic meter background PM, which is considered not photosensitizing, not capable of generating triplet at all. And I found that it can contribute to like 20 to 40% of the soil formation relative to H2O2. And more importantly, upon the 5 severity increase that I increased the BBOA concentration to 40 microgram per cubic meter, it of course reduced the availability of the actinic photon flux. But somehow, we still observe that the contribution of BBOA photosensitization to soil formation increase and even prevails over the typical H2O2 pathway in some regions like Athens. Okay, so when we have some basic information about how the BBOA or light-absorbing particles may interact with the gaseous molecules under sunlight, we also want to look into what is exactly happening inside the particles. So typically, because the BBOA particles is rich in organics, the reaction between the triplets and organics reasonably forming peroxides is worth taking a look. And like within my expectation, I found that the total peroxide determined by a calorimetric acid inside the particle gradually increase and rapidly increase when we have light and air, but nothing happens when there is no air, no light. That means the peroxide formation are largely attributable to the photochemistry inside the BBO particle, which required oxygen for propagating the reactions. And more importantly, when the classical view consider that the peroxide are predominantly formed in the gas phase, while the reaction triggered by the reaction of VOCs, forming radical first and then self and cross reactions of the HO2, RO2 radicals to form peroxide. This pathway is largely hindered when there is NOx. So specifically, the NO, nitrogen oxide, will take monoxide, will take the HO2, RO2 to like organonitrogen in competition with the peroxide formation. So quantitatively, people find that when there is like more than 1 ppb of NO, the typical MCM model will predict minimum peroxide formation. But somehow, even though we introduce up to 150 ppb of NO, we still see there is a considerable total peroxide left inside the particles, which means this pathway is quite interesting and unique, can persist under high NOx conditions. So I just want to brief the two major reasons in my analysis. So the paper is now in press. So first of all, the particular photolysis of BBOA afford very fast formation of HO2 and RO2, orders of magnitude faster than report for gas phase in terms of a single particle. Okay. And later, the NO actually is Henry's law constant, or let's say partitioning coefficient more accurately, of in the bulk phase of a typical organic particles are very low. That means when we estimate the mixing ratio, we just got a few in the bulk phase that cannot afford very effective or complete scavenging of RO2 and HO2. Later on, the peroxide formation as it is enabled. If we try to calculate the sink of HO2 by NO, we will be able to find that it is far below the sink by OM, organic matter. That means in the bulk phase, even though we have 150 ppb of NO, it is not sensitive to the HO2 sink. So rather, the HO2 are predominantly reacting with organic matters, which is also reported to form peroxides. Okay, so level glucosan, which has been widely used as a biomass marker, has become one of my next focus for its interplay with the BBOA triplet, and we found that it can the BBOA triplet can drive effective decay of the level glucosans, and more interestingly, we find that this pathway, I mean the BBOA triplet, the contribution relative to OH multi-phase OH uptake, which is considered as a dominant pathway for the level glucosan sink, increase upon RH decrease. So the scenario is very interesting because upon RH decrease, the particle is getting viscous. It limits the uptake of gaseous OH, but somehow the BBOA triplets driven by the light absorbing or let's say chromosomes inside the particle, which has been already neighboring the level glucosan. Upon light absorption, they become excited states and quickly react with the level glucosan and lead to very effective net decay of it. Okay, to sum up, so the principle of my research is that there is an increasing people considering the brown carbon aerosols largely emitted by biomass burning, or let's say wildfire, can absorb light and scatter light, causing the climate impacts. But if we have like such a magnifier looking into something happening inside the particle, we will be able to know that the light absorbing is indeed physical-chemically the excitation of the molecules. That means something energetic has been formed, and our research try to tell a story that there is also important chemistry within the particles that drive the secondary pollutants formation, which warrant further investigations. Okay, so thank you so much for your attention, and I also want to bring my sincere acknowledgement to both the organization team of ECR-iGAC-iCACGP, as well as my supervisor, Professor Chek Chen, who provide both financial and intellectual support to my work, and also a few of my colleagues that provide useful suggestions in telling the stories. Thank you so much, and I'm happy to take any questions.
Thank you. Thank you so much, Zach. That was a very interesting topic. So I had this question. Are you considering putting this concept of triplet excited states into a CTM, or do you have plans of doing something of that sort and see how the model works?
Oh, okay, sorry. So CTM is the transportation model. Am I correct? Chemical. Oh, yeah. So actually, because I don't have that much time to cover, we are working on how to parameterize these processes in a typical model. So why two ways? One is uptake coefficient, one through the typical aqueous phase chemistry. We try to derive the reactive reaction energy for reactions and the energy barrier. So at the end of the day, we have reaction rate constants. So this is also a paper that done by my colleague Chang, and the paper has been now the data is in press. So we develop a machine learning method to do parameterization for diverse organic molecules.
Okay.
So I believe this is maybe a useful step as a first step. Thank you.
All right. Let's see if we have more questions. Okay, so looks like there are no questions. We will leave your email ID to the participants, so if they have any questions, they'll ask you. Thank you very much, Zach.
Perfect. Thank you.
Thank you. Okay, so next up we have, hold on. So we have Dr. Diana Pereira. Dr. Diana Pereira currently is a postdoctoral researcher at the University of Helsinki. She completed her PhD at University of Paris City, where she studied the chemical composition of secondary organic aerosols. Dr. Pereira's presentation will focus on molecular markers used to characterize secondary organic aerosols, combining chamber experiments and field measurements in the greater Paris area. Please welcome Dr. Pereira. Hello.
So hello everyone, thank you for such a nice introduction. I'm trying to share my screen and then to start. So please let me know if it's okay.
Yeah, we see your slides.
Okay. I'm just looking for the pointer. Okay. Well, so today I would like to talk about the secondary organic aerosol and a way to address the chemical composition of it. So, as you may know, in the atmosphere we can encounter that we find different gaseous and particle components that can be originated from both biogenic or anthropogenic sources. And among them, we can find some volatile organic compounds that undergo through a series of oxidation reactions that modify their volatility. And because of this transition in the volatility, some of those species are able to partition into the particle phase, forming what we know as secondary organic aerosol. So then the importance of understanding or analyzing those particles relies on their capacity to influence the climate due to their transformation properties, also the influence of the radiative balance, and also it has been shown that they can have an impact on the air quality and human health. So we have some kind of information regarding some SOA precursors that can belong to the biogenic or the anthropogenic group. So for example, in the biogenic group, we can find some isoprene contributions followed by monoterpenes, among others. And then when we talk about the anthropogenic contributions, we can find some alkane followed by aromatics and others. So although there is a wide variety of sources that can contribute to SOA, it's important to highlight that not all of them have the same capacity to form the secondary organic aerosol. As for example, it has been shown that in urban areas, for the different species that were determined from the volatile organic compounds, the aromatic one, highlighted in the sky blue, showed the highest potential to form secondary organic aerosol. So this highlights that depending on the location we have, some of those precursors will be more important than others, and then they will influence in a different way the SOA formation. So following this idea, there are different studies that have been performed around the world in order to determine the contribution of both biogenic and anthropogenic species to the OC. So for example, normally the biogenic contribution is addressed in terms of isoprene, pinene, and others, while the anthropogenic one is normally associated to toluene, which is represented here, the monoaromatic contribution. So this study summarized the contribution of those species in different types of environments, going from urban to remote areas. And what I would like to highlight here is that if we focus our attention on the European region, we can observe that until that point, the number of studies was limited. And then the information that we had regarding the chemical composition of the secondary organic aerosol was related only to the biogenic compounds, and not because the anthropogenic were not contributed, but because it was it's hard to understand their contribution by determining markers, etc. So this plot shows that we need to better understand the contribution of the anthropogenic emissions. So this was the main motivation for the study I'm going to show you today, where we aim to determine the contribution of different VOCs to the OC with a focus on the Paris region. And for that, we took as an area of study 2 locations that I will describe more in detail during the presentation. So there are different ways to address the contribution of different SOA precursors to the OC. However, in this study, we focus on one of them, that it's the SOA marker method. So this methodology tries to create a direct link between the VOC and the SOA through the identification of specific oxidation products that we are going to call from now on as markers. So this methodology combines chamber experiments and field measurements in order to create this link. And for example, the main objective of the chamber experiments is that we can follow a single VOC oxidation, then we can identify the markers associated to that oxidation and also the amount of secondary organic aerosol that is formed. And having this information, we can then retrieve some mass fractions that will be then used in the field to perform the corresponding apportionment. So then, once we have this information from some chamber experiments, the next step is to go into the field to measure the markers in the real atmosphere and then to do the apportionment. So now I would like to go in detail in each of these sections, and for that I would like to start with the chamber experiments. So for this study, the chamber experiments were performed on the CISAN chamber, that is a stainless steel reactor placed here in Paris, which has some advantage. For example, it allows you to perform heterogeneous reactions under controlled conditions of relative humidity and temperature, and it also has the capacity to perform experiments under artificial realistic irradiation conditions. So for this particular study, we followed the photooxidation of toluene, ethylene, and naphthalene at different experimental conditions with a specific focus on understanding the relative humidity, the influence of the relative humidity on toluene photooxidation. So why toluene, ethylene, and naphthalene? So we selected those because they are normally associated as the most abundant aromatic VOCs observed in the atmosphere, and also because of their ability to form SOA. And why we wanted to better understand the role of the relative humidity? Because currently there are some observations that report the mass fractions for those compounds for the oxidation products. However, when we talk about them, there is a mixture of variation of different experimental conditions, and that's why we wanted to isolate the sole role of the relative humidity. And also, it's important to highlight that previous experiments normally perform the oxidation of toluene with low values of relative humidity. However, as you can imagine, when we go into the field, we can encounter higher values, and therefore it's important to understand its role. So how those experiments look like? Well, here we have the chamber. So the chamber is basically a reactor on which we need to add all the components that we want to start a chemistry. So, for example, we use ammonium sulfate seeds to favor the SOA formation. We also need to add the oxidant source and then the VOC. And after a period of stabilization, we start the experiments. So during the experiments, different instrumentation is connected to monitor both the particle and the gas phase. And one example of this, we can observe it here. So for example, we have the time series for the whole experiment for the VOC, which is represented in this black line, or toluene in this case. And then we have the particle composition in terms of the different fractions obtaining from ACSM measurements. So once we have everything that we want to see inside the chamber, the next step is to turn on the lights of the chamber to allow the photolysis and to start the chemistry. So what happened here in the profile? We can observe that while there is an increase in the VOC concentration showing its consumption, there is an increase in the organic fraction showing the formation of the organic aerosol. So here we were able to observe some aerosol formation at bulk level. However, to understand the role of the markers and determine their contribution to SOA, we need to provide further analysis at molecular level. And to do that, different filters were collected during the experiments, and then we performed some analysis by making use of different chromatographic techniques coupled to mass spectrometry. And after those filter analysis, we observed the following. So here we have the three VOCs under study, and we were able to derive the fractions for some ring retaining and some ring opening products. So for example, for toluene, we can find mainly nitrophenol compounds. And then for the ring opening group, we were able to observe the HOP8 and others. So normally the HOP8 is the marker that it's associated to toluene, and also it can be observed after the ring cleavage of others, so it's mainly associated to the monoaromatic fraction. So now that we have those markers, the next step, as I mentioned before, is to understand the role of the relative humidity. And to do that, we consider some specific experiments on which we try to follow the same experimental conditions, but varying the relative humidity from a value of approximately 5 to 40%. So here we have the example of what happened with the ring retaining products such as methyl nitrophenol. And we can observe here that when we have the dry conditions, we observe, let's say, a value around 0.07 for the mass fraction. And there is a decrease on this mass fraction when there is an increase of the relative humidity. So what happened with the other type of compounds, such as the ring opening? So here we have the DHOP8, and we can observe that there is a similar tendency to the one of the ring retaining products. And we observed that this decrease was approximately 5 times for both of them, showing that there is an influence of the relative humidity. So, as I mentioned, the DHOP8 is normally used to address the contribution of the monoaromatics. So there are some studies that are reporting its mass fraction. So then we wanted to compare the values that we retrieve at season chamber in order to see how much they vary from what is already reported in the literature. And we can see here that the value we observed was higher, and that also from the other studies, it seems to be a dependency on the experimental conditions. So what is the impact that the use of those mass fractions can have? So for example, if we take a specific data set and we apply the different mass fractions observed in the literature, we can see that depending on the mass fraction we select, it's associated to specific experimental conditions, we can end up in the over or underestimation of the contribution of monoaromatics to SOA. So then we need to be careful at selecting the appropriate mass fractions. So now that we are seeing that there is an influence of those mass fractions, and that also we are seeing a first example of the contribution of toluene to SOA, I would like to switch into the field measurements and talk about the contribution of the different SOA precursors. So for that, let me introduce you the cross campaign. So the measurements for this study were performed during this campaign. That was a field campaign that occurred in the summer of 2022 in the Paris region, which aimed to combine some ground measurements and some aircraft measurements in order to determine what happened when there is the encounter of biogenic and anthropogenic air masses. And for that, measurements were performed in different urban, semi-urban, and rural areas of the Paris region. For this particular study, I'm going to focus on the chemical composition of the particle phase from samples collected at two sites. So in one hand, we have the Paris area that it's accounting mainly for the urban emissions of this densely populated city. And then we have also the forest of Rambouillet, where we expect to have mainly contribution of, mainly biogenic contributions because of the density of this forested area. So in both places, PM1 sampling was performed during the young night, also to understand what is the influence between the chemistry of both day and night, and to see if there is an influence on the chemical composition. So with this, in order to see the chemical composition, we started with the OC and EC concentrations, and also the concentrations of some pollutants. So here, I would like you to focus on the upper panel, where we can see in the blue colors that for Paris and for Rambouillet, for the period of data overlap, although they both represent a different environment, we can see similar concentration values, and we can observe also a similar tendency during the measurements. So this was not the case of the EC concentrations, as we observe higher concentrations, for example, here for the urban area, which we associated to the local anthropogenic contributions. So to better understand difference into the chemical composition at molecular level, we selected some specific set of samples that were accounting for different conditions. So for example, we can have the background set where we have OC concentration values that are below the mean value, and also they are followed by low concentrations of pollutants, such as, for example, in the case of NOx. Then we can see that there is an increase into the OC concentrations while we go into the pollution 1 and pollution 2 periods, and also we can see that there is an increase on the pollutants. So now we want to see what is the chemistry, what is the difference on the chemical composition. And to do that, we made use of high-resolution mass spectrometry analysis, and then from the different formulae that were identified, they were classified in function of the different heteroatoms in the following 4 families. And here we have the contribution of the different formulas classified for the Paris profile for the 3 different periods. So let's focus our attention on the background period. So first we can see that there is a predominance of compounds containing nitrogen. And while we go into the pollution period, it seems that there is still a predominance of compounds containing nitrogen. So what happened when we check the same profile for the forested area? So again, let's focus on the background period, and we can see that the tendency is not the same that Paris, As in the first samples, we have a predominance of compounds containing just carbon, hydrogen, and oxygen, highlighted in this sky blue. But when we go to the pollution periods, we see that the tendency seems to be more similar to the urban area, as we have again the predominance of compounds containing nitrogen, highlighted in brown. So here we were able to observe a first difference into the chemical composition at molecular scale, which was mainly associated to the background period. However, what happened with the molecular markers that we were trying to follow before in the chamber? Let's talk about them to see in a more quantitative way what is the difference into the chemical composition. So because of the time, today I'm going to show you just some examples of some anthropogenic and biogenic markers. So here we have two of the markers. So we have the HOPA that, remember, we were using to follow the monoaromatic contribution. And then we have phthalate acid that we also observed in the chamber that we were using to follow the naphthalene contribution. And again, we have the profile for Paris and the profile for Rambouillet. And we have here the background and the pollution and pollution 2 periods. So first of all, it's important to highlight that in the case of the HOPA, shown in blue, we see that they have similar concentrations, although one is a urban area and another one is a forested one. And then when we check the phthalic acid contribution, we observe that it's mainly present on the urban area. We can also observe that there is not a clear difference between the concentrations of the different periods as they seem to be similar between the background pollution 1 and pollution 2. So the fact that we observe those markers not only in the urban area, but also in the forested one, shows that there is an influence on the anthropogenic inputs in both types of environments. So what about the biogenic markers? So for example, I am showing you here the profile for cis-pinonic and pinic acid, which are associated to pinene, again for both Paris and Rambouillet. And then we have the background and the pollution periods. So what I would like to highlight here is that we have higher concentrations in the forested area that we associated with the higher density of vegetation that it's observed in the area. Also, we can observe a clear difference between the background and the pollution periods, as the concentrations are higher for the pollution. And we can also observe that there is a different contribution between day and night samples, where the concentrations are higher during the nighttime that we associated with the nighttime chemistry. So now that we were able to observe some difference and we determined the molecular markers both in the chamber and in the field, the next step, the final step to summarize all this, is to combine those values by using the SOA marker method that was first introduced in order to reply what is the contribution of biogenic and anthropogenic precursors. And after doing that, we obtain the following profile. So here we have the OC composition in terms of the different fractions. So we have for the biogenic fraction, pinene and isoprene markers. And then for the anthropogenic one, we have toluene that is representing the monoaromatics, and we have naphthalene. So first of all, if we check both profiles, we can see that in the forest of Rambouillet, we have a higher contribution of secondary species. Then when we talk about the contribution of the biogenic one, we can observe that there is a predominance in the nighttime samples of the pinene contributions, and then it seems to be the isoprene fraction contributes the most in the biogenic one, also for the Paris urban area. And then when we talk about the anthropogenic ones, we can see that there is a predominance in both from the monoaromatic contribution, which seems to be equal in both sides. And then naphthalene, it's mainly observed in the Paris urban area. So with this, I would like to highlight the main observations of this study. So first, when we were talking about the chamber experiments, we were able to see that there is an influence on the relative humidity in the photooxidation of toluene, which then has an impact in the HOPA that is normally used to address the contribution of monoaromatics in SOA. And therefore, it's important that we consider the good experimental conditions in order to properly address their contribution to SOA. Then when we switched to the field measurements, we were able to see that there is an influence of the anthropogenic and biogenic emissions in both urban and forested areas, and that the main difference between both sides was observed mainly for the background period. And then finally, this work highlights that there is an influence of the anthropogenic emissions into forested environments because of the presence of compounds containing nitrogen, and also because of the presence of these aromatic compounds and the markers such as the HOPA that we observe in both with similar concentrations. So with this, I would like to thank you all for your attention. Here are the emails in case of any content. I would like to thanks to all the people that made this work possible and all the funding, and I will happy to take any of your questions.
Thank you so much, Diana. So we have a question from Milan Roska. So it says, which ionization methods did you use for your MS analysis in the chamber? And could humidity dependency in the sensitivities of your instruments affect your results?
Okay, so mainly, let me go back to the chamber. Okay, so to do the analysis, we use offline by collecting some filters. And then we use mainly three techniques. We use orbitrap analysis, liquid chromatography coupled to mass spectrometry, and GCMS. So for the orbitrap and the liquid chromatography, we used an SE source. So we were not fragmented at all. And then for the GCMS, we were using we were using an electronic impact source. And then for the influence of the relative humidity on the online measurements, yeah, there could be an impact. However, for example, for the ACSM, if I remember well, there is a dryer at the inlet of the instrument, and then for the SNPS, it was similar.
Right, and we have one more question from Max. Hold on. So he wants to know on slide 19.
19.
On slide 19, is spinine a proxy for all monoterpenes, or is it likely a lot more species are therefore missing? Or is it likely a lot more species missing? I think that's what he means.
Yeah, so normally we are saying spinine, but it's not for all the monoterpene because we are only considering three markers that are the pinic, the cispinonic acid, and the MBTC8. So we should consider more markers in order to have the whole contribution of monoterpenes.
Any more questions that we get, we will direct it to you, Diana. So thank you so much for the engaging talk. We will go ahead. We'll go ahead with the next speaker. So next up we have Dr. Ezekiel Vaiguru. Dr. Ezekiel Vaiguru is an environmental scientist specializing in atmospheric pollution with expertise in air quality modeling. Dr. Vaiguru recently worked on air quality assessment in East Africa, focusing on Nairobi, Kenya, using integrated satellite data and atmospheric modeling. He will share his findings on pollution hotspot and seasonal variation in the region right now. So let's welcome Dr. Vaiguru.
Okay, thank you for the introduction. So, hi everyone. I'll be sharing about the study which we did during my PhD at University Paris Cité. And first and foremost, I would like to recognize Dr. Matthias Bickman, Dr. R. Subramanian, and Dr. Guillaume Sawa, whom we worked together during this project. So, as we can look, air pollution is a major risk to health, which is associated with different kind of diseases ranging from stroke, heart diseases, and various types of cancer. And worldwide, air pollution has been attributed to cause about 7 million deaths, and sorry.
Sorry. Ezekiel,
Okay.
your screen is not on presentation mode. Could you? Yeah. Okay. Thank you.
Yeah, I think, sorry, yeah, it's so on the African continent alone, we have about 1 million deaths occurring each year due to air pollution, and about 700 of these are due to indoor exposure, while about 400,000 is due to ambient exposure, and mostly these deaths are due to PM 2.5 pollution. So looking at the African continent, but particularly for a city like Nairobi, we have due to growing population and increasing economic activities, we have also increasing sources of emissions, which range from open burning of municipal waste, biomass fuel, which is in most of the informal settlements where people have no access to things like electricity for cooking or LPG gas, so they use wood fuel and charcoal. We also have a lot of vegetation cover in northeastern part of Nairobi, and this is a forest called Karura, which is just close to the city, and this is a major source of organic aerosols, which also affect air quality in the city. So traffic is another important source of pollution in the city, and this can be looked in different ways because most vehicles that are imported in the country are majorly second-hand, having been used in their or the places of origin. So currently in Kenya, we have had these policies that a vehicle should not be more than 8 years old when it is imported. So we find there is a lot of challenge because we get a lot of these second-hand vehicles, and due to their different uses. So the major mode of transport is by road, and we have these different kind of smoking vehicles, lorries. They are majorly used for transporting of construction materials in different parts of the city. Then we have vans, which are used for public transport, and we have also another growing sector of motorcycles, which are used for the last mile connection, and that we have quite a lot of them, estimated to be about 1 million in the country, and a huge number of that is in Nairobi. As also we have another important sector which contribute to air pollution, which is industrial activities, which are found. We have small scale industries also being found in the residential areas. So while we have all these sources of emissions and high pollution, as we have seen, one of the major challenges that we find is a huge data gap. We have limited data, especially for the region where we were doing this study, and we find that most of the measurements which are being done are either short time for different groups which are do short-term campaigns, different research group, and then we have these measurements running for a short period, then some breaking. So that is one of the challenge that we have, the scarcity of data. So in this study, our motivation was to led by the high pollution in the city of Nairobi, which is driven by growing population, heavy traffic, residential emission, and also industrial activities. Yet the specific sources and transport pathways of pollution have not been understood properly. So in this study, we used different sources of data. So we integrated ground measurement, satellite, and modeling to be able to understand, the air pollution in this city. So for the ground measurement, we had several sites are distributed, across the city. And this campaign was, started in 2020, and it ran all through up to 2022. So in 2020, during the COVID lockdown period, so we had all these sensors located in one place. But later I was able to find sites which are representative to different setup, kind of different areas depending on the emission sources. And in 2021, I deployed the sensors in those locations, where I was able also to co-locate the sensor with a reference instrument at the University of Nairobi. And then, I performed calibration. So we had also some measurement running at the US Embassy, which I think that is the longest measurement site which exists for the city, even currently. So with this 3-year period of measurement, I was able to do a different kind of an analysis to be able to understand, the long-term characteristic of PM2.5. So I was also able to get MIAC AOD data, which I used in the model evaluation, and this was for the year 2021. And then the modeling used in this case was the Wolf Shimel, which I was running, and I set up the model, and in this case, I show the different data requirements that the model takes. So one of the requirements, very important in this case, is emissions for which are specific for the region of the study. So in this case, we don't have high resolution emission for a city like Nairobi, and therefore we are dependent on CAMS global anthropogenic emissions, and also CAMS fire emissions. So with the CAMS emissions, we also had the Dachua emissions, although it's not integrated in Chimel. So I'll be showing some comparison with the emissions that we had. So we also set up the simulation domain, which covers the entire, maybe the eastern and part of Central Africa. This is one of the important region due to dense vegetation, and therefore we had this expansion of the domain. Then we had an intermediate domain which still covers the region of interest, and then we nested the model domain over the city, the region where we have the city of Nairobi. So these domains are, we had the coast domain at 30 square kilometer, the intermediate at 6, and then the nest was at a very high resolution of 2 kilometer, which is possible for Shimel. Then we had the weather data, and in this case is from WAF, which is used to drive the model. And also the model also requires land use data to be able to distribute the emissions over the simulation domain. So then we have different schemes for secondary organic aerosol. In this case, I use the standard scheme, which is in Shimel. So then I used the measurement, which I've just shown, this surface measurement from the different sites in Nairobi to evaluate the model, as well as the MIAC AOD. So in this case, now I show the long-term measurements of PM2.5, the surface measurement at 2 sites which were running for the, between 2020 and 2022. So here we find that the PM2.5 concentration tends to increase in January to February and decrease in March to May, and then rise again in June to September, and the decline, and then we have a decline in October to December. And this pattern is inversely related to Nairobi rainfall cycle, as we can see in this case, and it remains consistent over the 3-year period. So looking at the citywide variability in PM2.5, so these are the 6 months that we had all the sites, the sensor running at all the sites. So we find that the PM2.5 levels vary significantly across the different locations, showing high spikes in traffic areas and lower levels in suburban areas. Also, the PM2.5 levels peak from July to September. This is the dry season, during which also the wind speed are low. So we have low dispersion at this during this period, and therefore there is possibility of accumulation of the local air pollution. So looking at the diurnal characteristic of PM2.5, we find that the traffic as classified, we have traffic related sites, we have urban background and suburban location. So, and in this case, we find that the traffic site have two pronounced peak in the morning and another one during the evening. And these peaks are related to the traffic rush hour period. And then we have a low concentration during daytime due to the expansion of the planetary boundary layer height, which causes dilution of PM2.5. So looking at the urban background and suburban site, we find that we only detected a single prominent peak at the evening, which is related to residential activity. So in the morning, we find that the PM2.5 levels don't peak, and we can only see a peak in the evening for the urban background and also for suburban site. So the peak concentration and their timing show significant variability across the different type of site that we had in this case. So now looking at the model evaluation with the MIAC AOD, and in this case, I only show for images for 1 month for January, although we have this analysis running for the whole year. We find that the model successfully simulates MIAC aerosol optical depth, both seasonal and spatial pattern, and the model reproduces high January AOD values resulting from biomass burning in areas like, in this case, we have Uganda, Tanzania, and this is Kenya. So in the north or western part of Uganda and also in central Tanzania, we have high levels of AOD, both in the model and Chimel, and this was attributed to fires which break out during this season. And this has also been reported in previous studies like in Boyo, and also we have Idrissa, who also did a study before. So the model underestimate the overall AOD, which is in agreement with the values reported by the study of Idrissa, but he used a different model in that case, that is WolfChem. So now looking at the simulation of the three, different domains that we have in this simulation, we find that all simulation show a strong PM2.5 concentration gradient between Nairobi and the surrounding areas, which is also consistent with the finding in Mazeo et al. 2022, but also, only for the Mazeo study was only for 1 month between March and February and March 2017, but that is maybe the only study which focuses on Nairobi, but also it found a very sharp gradient between the regional and the local air pollution for the city. So the differences become more pronounced as the model resolution increases from 30 to 2 kilometer, and maybe at 30 kilometer, that the domain resolution is very close, and we can not be able to see, the different features, since the emission inventory used in this case is at 10 kilometer resolution. So as we go down to high resolution of 6 kilometer, we find that we can see the, the differences in, the spatial distribution of PM2.5, although no much difference with the 2 kilometer resolution, since the emissions in this case are still, very close, and that now shows the need maybe to have a high resolution emission for this city. So looking at the model evaluation, so we find that the course model resolution showed the best performance with strong correlation and low error for the CAMS version 4.2 emissions, which have been used for the long-term simulation, although we had other test simulation with other different types of emission for 1 month test, which now is the basis of this comparison. So the one used for the entire year is the CAMS 4.2. So we find also that the final resolution of 6 and 2 kilometers increases the error, shifting the bias from underestimation to overestimation. And the CAMS version 4.2 performed better than 6.2. So now, if we look at the seasonal changes in PM 2.5 across, the over the 6 kilometer resolution domain. So we find that during the dry season, Nairobi PM 2.5 pollution is high in the northeastern area. This is due to high population in this region. Traffic, also we have a lot of traffic because one of the major road networks cuts across that region. And also we have industries, small-scale industries found in the residential areas. So local sources are the primary causes of air pollution in Nairobi, with regional sources having a minor effect, as can be seen. So we have a hotspot across the entire year. We have a hotspot on Nairobi, but largely we have very clean background, maybe of about 10 microgram per cubic meter. So now, if we look at month by month variation at one of the urban background sites that we had during our campaign, we find that the model accurately represents the monthly PM 2.5 variation, except for May and June, but consistently overestimate the concentration throughout the year. So now if we zoom closer to the city and now looking at the different types of sites that we had during our campaign, we find that the model exhibit a spatial bias of estimating values near the city, which is at this location, the city center, and in sites like KUCC, UON, and IPA, which are all close to the city center, but it really underestimated the metropolitan areas such as Ngong. So now looking at the chemical composition of PM 2.5, we find that organic aerosols are the main component, comprising over 2/3 of the total PM mass, while inorganic aerosol and black carbon only make about a quarter of the total PM 2.5 mass. So the next question, although we one of the challenges that we didn't have, a speciated chemical PM 2.5, speciated measurements. So we look at the emissions and see which are the important emission sector which contribute to this PM 2.5 that we have seen. And in this case, we compare the CAMS version 4.2, which has been used for the long-term simulation, and the Chiwa emission, which is a regional African specific emission inventory. And in this case, we find that the high emission in northeastern Nairobi, which it matches PM 2.5, a spatial distribution pattern, which has been also observed in the model, and is likely due to dense population, traffic, and industrial activity, while residential emissions, in this case for the CAMS emission inventory, is the most dominant in this case. So followed by industry and traffic. And for Dachua, we see the consistency. Also, residential emission makes the larger portion of that. And this now is also consistent with the observation whereby we have seen that in urban background site, we have a prominent single peak during the evening, which is due to residential emission. So the Dachua inventory here appears to overestimate the residential OC, but now this the simulation with Dachua inventory needs also to be tested with the model. So the major takeaway for this study is that air pollution in Nairobi is primarily from local sources, mainly from residential emission, while PM2.5 levels are highest in traffic areas and lowest in suburban areas. And PM2.5 concentrations are highest during the dry season. That is inversely related to the rainfall pattern for Nairobi, while organic aerosols are the main component of PM2.5, and it makes up about 2/3 of the total PM2.5 mass. So as part of the future work is that we need further refinement of the Nairobi urban emission inventory to improve on the model performance at finer spatial resolution, and also to explore new emission inventories to address the model of underestimation biases. And in this case, maybe we need to test a regional emission inventory like Dachua, and maybe have a specific, also Nairobi urban emission inventory, as just mentioned, and to conduct measurement of PM2.5 chemicals position to be able to pinpoint sources and the effects of the simulated PM2.5. So as part of this study, we have published a paper which is Nyaga et al. 2025, and we are also in the process of publishing the second one, which now involves the simulation work. So thank you for your attention. Maybe I welcome questions. Sorry, I can't.
Thank you, Ezekiel. So we have a few questions for you. So the first question is, what is the reason for model underestimating AOD in your work and the earlier studies? Is this driven mainly because of reliance on global anthropogenic emissions that could be underestimating precursor emissions in African cities?
Okay, yeah, so that is thank you for that great question. So the reason that we find that the modeling studies are very limited in this region, and therefore a model like Shimel, which has been used in this case, I think this maybe is the second time we are evaluating Shimel. So there are various reasons can lead into that, and maybe that one of them could be also some numerical problems in the model, so that it underestimates the AOD. And yeah, I think that could be one of the major reason. And also we have the fact that we are using global emission inventory, which also are not fine-tuned to the emissions which are specific for this region.
Right, and we have another question from IRC. He wants to know, what hypothesis do you have about the better statistics for the coarse resolution cases in your evaluations?
So the reason for that, we tend to find that the coarse model performs better than what we get as we move down to high resolution, and this could be attributed to mainly to emission inventory, because as we have noted is that this global emission inventory tends to the model can only see very high emission at the Nairobi CBD. So we could be having an issue with how the emissions are distributed in the simulation domain, and for the coarse model domain, it's only seeing a few grid cells of that over the city. But if we move very close, we have, very many grid cells. And in that case, we see that all emissions are, within the city, and outside the city, we find that maybe we have very low, and maybe also we need to update to see whether, with the growth of the city, we have, the emission sources distributed, in the metropolitan areas of the city, and then maybe we have to check whether they are well simulated.
And IRC has one more question. He wants to know if you had thought about data assimilation for this work. He says you had already mentioned scarce measurements in the sites. Have you thought about using data assimilation, for example, for estimating better model emissions? I think that's what he means.
Yes, so the scope of the work that we did, that was not within the scope at that time for my thesis, but currently we also have formed a network which we are looking particularly on Nairobi urban emission inventory. So that is one of the things that we are looking into, and the next. So if we want first to develop high resolution emission inventory for Nairobi, and then with that maybe we can move to also applications of data assimilation, and also maybe some machine learning, so that we can compare and see that whether we have some improvement in the estimation of PM2.5.
Okay, and Karun has another question. He wants to know, could the underestimation or overestimation biases be linked to the differences in the physical schemes used in WRF?
Okay, yeah, that's a great question. I think we, although I've not shown the results for that, but I tested both, the two different, the standard Shimel scheme and the VBS scheme, and we find that if maybe I don't have a figure for that which shows the Diano profile, so we find a slight improvement on the profile. The standard scheme overestimate compared to the VBS, but then we find that there is no much improvement. But also this scheme need to be tested, so we don't have measurement to really test also the scheme. We need, still more measurement to test them.
Okay, and there's one more question. This is from an anonymous sender. He wants to know, okay, how does your model do boundary conditions at the edges of the core's outer domain? How is transboundary pollution from outside the outer domain represented?
So the outer domain. So we use the CAMS global model for that, for the for the boundary condition, which I now runs, it drives the CAMS global model is the one which is used in the model to drive the model, and then now we have the WRF Shimel for metrology for the model.
Okay, and I don't think we have any more questions. Thank you so much, Dr. Ezekiel Vaiguru. And I would like to thank every other speaker who has been here with us, who's given us engaging presentations and talks for us today. I would also like to thank the attendees for being engaging. There